So, welcome to the 10th tutorial session of problem solving through programming in C. This is a SWAYAM course floated by Professor Anupam Basu from Department of CSC IIT Kharagpur, and I'm Siddhant. I'm the TA who is in charge of taking these tutorial sessions, where we will discuss the concept and few example questions, which might help you out with the assignments as well as the final exam. So, in this particular session, we will be discussing uh, the bubble sort method. We had discussed in the previous session regarding the selection sort and insertion sort. In this particular session, we will discuss about bubble sort and see the time complexity, the best and the worst time complexity of bubble sort, and then we will look at bisection method and what does bisection method do, and so on. And then we will have a brief look at pointers. So let us jump into the session. So first, like I have, yes, yeah, sure, I'll do that. Um, okay, so yeah, so let me start with bubble sort. So like the usual way we do for the selection sort and the insertion sort, we will also calculate the best and the worst case time efficiency for bubble sort. So just to remind you, uh, we had discussed selection sort and insertion sort in the previous lectures, and the best case time efficiency for selection sort was O of n square, and the worst case was also O of n square, and the best case for insertion sort was O of n, while for the worst case was O of n square. Okay, so you just have to remember all this, but you also need to know how to derive this. So now let us look at bubble sort. So now we will take a similar approach like we took in insertion sort and selection sort. So let me take the same matrix. So the elements were 1, 3, 4, 5 and 9. So it is a array of 5 elements. So for deriving the best case efficiency, what do? We take an array which is already sorted. So let me say that I want to sort in ascending order. Okay, in ascending order, and then like I'm assuming that I want to sort the array in ascending order, and this is my array. So the best case efficiency would be when it is already sorted. So this is the case where it is already sorted. So it is already in ascending order like this, and then we'll look at the worst case efficiency, and worst case efficiency would be when it is just in the opposite order, that is it is in descending order and we want to sort it into ascending order. Okay, now let's have a look at each of this. So let's start with the best case. So in if you know how bubble sort works, let me just give you a brief overview. So first we take the entire, so we look at the entire array. We will and we will compare all elements starting from the top. So we will compare 1 and 3, then we will compare 3 and 4, then 4 and 5, and 5 and 9, and we will swap whichever is higher so that it goes below. Okay, uh, probably it will be better if I start from the worst case so that you can see the bubble sort working. So first I compare, what I do is I compare 9 and 5 and I switch them because I find out that 9 is greater than 5, so we just put the heavier element down. Okay, so that will lead to something like this: 3 and 1. Now next we compare 9 and 4, and again I do the switching, so this will become 5, 4, 9, 3, 1. Then next what we do, we compare 9 and 3 and we do the switching again, so it will become 5, 4, 3, 9, 1. And then again we look at 9 and 1 and we switch them, So we compare them and then we switch. So it will become 5, 4, 3, 1, 9. So 9, the heaviest element, went to the bottom. Okay, so this is so what I did here, how many operations did I do here? I did 4 number of comparisons and 4 number of swapping. So I did 4 compare or 4 conditional, as I have said earlier, and 4 swapping. Okay, now this is my array. So I'll start from there again. I'll just rewrite it here. uh, 1 and 9. Now I look only in this first 4 elements. I know that the heaviest element has gone to the bottom, so I just look at the top 4 elements. Now I check 5 and 4 and I do the swap. So this becomes 4, 5, 3, 1, 9. Then I look at second and third element and I do the swap again. So that brings you to 4, 3, 5, 1, 9. Then again I look at the third and the fourth element and I swap. So that will bring me to 4, 3, 1, 5, 9. So now I am convinced that the heaviest, two of the heaviest elements are at the bottom. Okay, so how many comparisons I did? I did 3 comparisons or 3 conditionals and 3 swappings here. Okay. Now next what I do is, I know that the last 2 elements are sorted, so I have to look into the first 3 elements. Okay. Now I again start comparing the first and the second element, and I see that there is it is not in ascending order, so I have to swap. So I'll swap them. So 4, 3, 4, 1, 5, 9. This is what we get. Then again we look at the second and the third element. So I compare them and I swap them. So you have 3, 1, 4, 5, 9. So now I am convinced that the last 3 elements are sorted. Okay, now only I have to look into the first 2 elements. So how many swap I have done here? I have done 2 swaps, 2 conditionals and 2 swaps, right? Now finally I know that the last 3 elements are sorted, so I have to look into the first 2 elements only. So I compare them and I exchange, I swap the values. So now we get 1, 3, 4, 5, 9. So now I realize that all the elements are sorted. So this is basically how it works. So here we have 1 swap and 1 conditional. So total of how many swaps did we do? So number of operations is, for a conditional, it's 4 plus 3 plus 2 plus 1 conditional, plus 4 plus 3 plus 2 plus 1 swaps. Okay, now if I have to write that, this is for a matrix of 5, for an array of 5 elements. Now if it is for an array of n elements, you can see that it will go from n minus 1, n minus 2 up till 1, this many conditionals, plus similarly n minus 1, n minus 2 up till 1 swaps. So you can calculate this. This is n into n minus 1 by 2 into 2, right? By 2 into 2. So this is n into n minus 1. That means order of n square. Okay, so the worst case time efficiency of bubble sort is of order of n square. Okay, let me write this down. So bubble sort, the worst case time efficiency is order of n square. Now what about the best case time efficiency? So we will follow the similar procedure for here. So we will compare the first 2 elements. We will find that they are sorted. We will compare the next 2 elements, sorted. And we will compare the third and the fourth element. It is no change required. And then we'll compare the fourth and the fifth element, no change required. So we just needed to do 4 comparisons, right? 4 conditionals. Now if you have written your code properly, we will see in the second question that we have. So if you have written the code properly, the code will stop here itself. Like that would be an efficient code. We will see what would be an efficient code, how to do that. So the code will stop here itself because there was no swapping taking place at all. So the efficient bubble sort code will stop here. But if you have done it in a way where it's not very efficient, then it can go and it can again check for this top 4 elements, then top 3 elements, and top 2 elements, and so on, which would not be the right way to do things. So the best case efficiency should be when you have written an efficient bubble sort code which stops the sorting procedure, stops if there is no swap in any pass. Okay, so the sorting should stop if there is no swap in any pass. So only it will stop in the first pass itself. It will just do 4 comparisons between 1 and 3, 3 and 4, 4 and 5, and 5 and 9. So number of operations is 4. There is 4 conditionals. That is n minus 1 conditionals, order of n. So best case efficiency of bubble sort is order of n. That is an efficient bubble sort. Okay, efficient bubble sort is order of n. Okay. Now, is this clear how we calculated the number of operations for the best case and the worst case for bubble sort? Okay. All right. Now I was telling you about the best case efficiency of bubble sort, like how to improve, the best case efficiency. The normal, if you do it in a very brute force manner, then the bubble sort efficiency, best case efficiency, would be n square. But if it is a efficient bubble sort code, then it should have a best case efficiency of order of n. Now let's answer this question, which will help us know what should be the what should be the bubble sort code which will give us order of n efficiency. Okay, so this question asks, how can you improve the best case efficiency in bubble sort? So best case means the input is already sorted, right? Now there are 4 options. Just have a look at them and think which could be used to improve the best case efficiency. That is, it should be in order of n. So that is, it will only go through the array once, and it will know that it is already sorted. You can take an example of the same example that I told earlier. So you can take this array as an example and just go through the code, and you can find out which would be the answer. So basically what you need to do is, you need to, like I said, the sorting needs to be stopped if there is no swapping taking place in any of the passes. So sorting should stop. So how to know whether swapping has taken place at all during all the comparisons and so on? So we define a Boolean data type called swap. So we have defined a Boolean variable called swapped. Okay, and we have set it to set true. Okay, now in the normal like the number of passes that we need to go. So usually what we would do, we would go and consider all the elements first, and then the top 4, then top 3, then top 2, and top 2, and so on, right? So here you can see the array should the outer loop j should go from arr.length minus 1. So basically it will go from 4, that is the index 4, up till the index 0. That means in the first for the first iteration you are considering all the elements. For the second iteration you are considering only the top 4 elements. For the third iteration you are considering the top 3 elements, and so on, right? And then we just add a with the and operation, we just add this swapped. So for this condition, so in for loop, if you remember earlier from when we covered the for loop, this condition is evaluated at the beginning of the loop always, right? So if swapped is true, only then this loop will start. So the first option is definitely wrong, because if we have set boolean to false, so the loop itself won't start. So what the loop needs to do in order to improve the best case is it has to go through the array once, do all the comparisons, and then it has to say that, oh, there was no swapping that took place, so now I should stop. So that is what the loop should do. Okay, but in option A, because you are setting the swap to false, and this conditional will be evaluated initially, this j greater than 0 greater than equal to 0 and swapped. So this will be evaluated initially, and the loop will not start itself. So definitely option A is not the answer, right? Now let's look at the other options. So what we do next is we set swap to false, and we use an inner loop to go from 0 up till less than j. So basically we go from, say, for the first iteration where we are considering the entire array, we go from 0 up till the fourth element, that is index of 3. Okay, so we go from 1 to 5. So, and what we do inside is we compare this particular element with its next element, and we switch if and we swap them if we find that they are not in order. So we in the first iteration of k, we go and check 1 and 3. Then the second iteration we go and check 3 and 4. Then 4 and 5, and 5 and 9. Right? That is what we do. And if there is a swapping taking place, we are setting it to true. So you can see that we need to set the swap to true, because if the swapping takes place, only then swap should be true, right? And that is being done only in option C and option D. In option B, you can see that the swap, we are setting it to false, but we are never making it true when the swap actually takes place. In this case, this will just run with the same brute force method that we were discussing earlier, right? So it will be order of n square, not order of n, because we have never set whenever, even if swap does not take place, if the swap if the swap sorry, this will stop only after one iteration itself, no matter if there is a even if the array is sorted or unsorted, it will stop after one iteration, because you are not setting swap to true anymore, even if there is a swap taking place, right? So the first iteration will be done, but in the second iteration again this conditional will be evaluated and it will stop even if the array is unsorted. So this algorithm itself is wrong, okay, because it will run only for one iteration. Okay, now A and B, both options we have crossed out. Now what about C and D? So there we now know that the swap has to be set to true if there is a swap taking place. So this is there. Okay, now the only difference in this two, in option C and option D, is swapped is set to false here, and here it is not set to, it is not, nothing is done with swapped here. Okay, so now say it is, the input is sorted already, right? If it is sorted, then this entire, if ARR k is greater than ARR k plus 1, this entire thing will never work because it is already sorted. So our previous element will always be less than the next element. So the if conditional will always be false. This part will never be executed. So if that is never executed, then here the swapped value will remain true because we have not set it to false. It will always remain true, and if it remains true, the iteration will keep going on. We will keep going into multiple iterations of the outer loop, which is not really required. So we need to set the swap as false. Only then, if it checks and it finds out that there is no swapping that has taken place, so here the swapped has never been set to true because the if condition is never satisfied for any of the iterations of the k loop. So the swap will still be false, right? And if it is false, then the code will exit after one iteration because this conditional will not be satisfied anymore. So this option C is our answer here, because the swapped, we are using this boolean variable swapped in order to check whether any of, if in any pass. So every pass is represented by this outer loop j. So in the first pass itself, we check that if there is no swapping that is taking place, then this swapped will give a false value, and the outer loop will exit. So this will give us a best case efficiency of order of n, because it only needs to go through conditional checks for n minus 1 conditional checks like we saw earlier. So this is the best case efficiency, the algorithm for the best case efficiency in bubble sort. So this is an algorithm for the efficient bubble sort. Okay, is that clear? Okay. Alright, so let's move on to the next question then. Now I have questions regarding like it will be over miscellaneous topics. There will be some questions regarding bisection method as well and pointers as well. But for now, let us look at some miscellaneous questions. Um, okay, so we have a void function. As you know, it's not returning anything. So void. It takes an integer x as input and it sets the integer to the value of 40. And we have a main function where we set we declare a integer variable y, set it to 30, and we pass it to this function, and then we print y. So what will be the output of the code? Yes, why do you think that 30 will be the output? Right. So this x that we have is a formal parameter, and whatever happens to the formal parameter until it is an address, it's just a value that, so here we are doing a call by value, right? Only the value is being passed to the function, not the address. So you are just changing this temporary formal parameter called x, the value of that parameter. So you're not changing the value of y at all, because this function is not returning anything. It is just changing a dummy value, dummy variable, the value of a dummy variable x. Okay, so basically this does not do anything. I mean, this particular function, it does not really do anything. So y value will still be set to 30. So here the answer is option B, which is 30. Right? Is it clear? All right, let's look at the next question. So now we have here a 2D array of type short. So short is a type of integer. Uh, it's a still an integer variable, but it has a smaller range than int. Okay. Now let's okay. So we have a uh, sort array variable, which is a 2D array, as you can see, and we have declared it as so. We have initialized the array as so, and printing we are printing certain values of the array. Okay, so what do you think will be the output of this code? So you have to remember that C uses a row major format for storing 2D arrays. That means if I enter, yes, uh, option C. Okay, we'll see what is the results here. So if you enter the elements, you declare the 2D array like this. So here it has 3 rows, right? This is the number of rows, and this is the number of columns. So if I write this array num, so it has 3 indices here. So let's say 0, 1, and 2, and it has 2 indices here. Right? It's something like this, as 0 and 1. So these are the columns and these are the rows. So it is like this, like 3 cross 2, right? It's a 3 cross 2 matrix. Now how this initialization is done is that you have 2, 5. Remember, it's a row measure. So first the first row will be filled up, then the second row will be filled up, and then the third row will be filled up. So you'll have 11, 17, 23, 28. So this is your 2D array. Now the first thing that you're printing is star of num plus 2 at 0. So when you say num, you are referring basically to the the address of the first row, the element at the first row, first column. That is the address of this element 2. Okay, that is what you are referring to. When you are saying it is star star num, that means you are saying that you are basically saying what is the value of num of 0 0. So now you are referring to the value that is stored in the first element, like the first element of the array, that is the first row, first column. So what is the value being stored in that particular element? Okay. Now here I have written num plus 2 of 0. That means how will that be evaluated basically for us? So it will be num of 2 of 0, right? Now what is num of 2 of 0? So let me write, it will be 23. So let me write before that, let me write this. Okay, now this is equivalent to saying num of a of b. Okay, now these two are equivalent expressions, they are the same thing. So similarly, if I say what would this represent? Num of what? Can you tell me? Right. So this would be num of 1 of 0. And what would that be? Right. So 11, right? So the answer is option A, which is first is 23, which is 2 of 0. The third row, first column, and then num 1 of 0. Second row, first column. So we have 23 and 11 respectively as answers. Okay, so it's basically a concept with pointers. So yeah, okay. So basically, how this all right. I'll explain it with say two and zero. This first thing. Okay. So first you are at num. Okay. When you say just num, you are referring to the address of the first column, first row element. That is, you are referring to this address at 0 0. The address, not the value. Okay. Now the first thing that you write num plus a, that is here num plus 2, that is basically the row notation. Okay, so basically I'm saying num to move by a units. So here I am saying num plus 2, that means it will move from pointing to 0 0 from to num plus 2, that is pointing to the third row, right? So it now came to the third row. Now next what I am saying is 0, index of 0, that means this b. Okay, this b is 0. So what I am saying is, okay, now I need only wherever you are already pointing, just tell me that itself. Okay, now if I had said say num of 2 the star plus 1 star. Okay, so what I said here, num was originally pointing to this. Okay, num was pointing to this element which was at 0 0. It was pointing to it stored the address of the element at 0 0. Now I said num plus 2, that means it will go on the rows first. So it will go to here. This is num plus 2. This entire row is num plus 2. Okay. Now I am saying plus 1. So I am putting the star so that I am representing this first star of num plus 2 represents the address of the first element of the third row. So basically I'm pointing to this 23 right now, like the address of this 23. Now then I say plus 1. So it will move along the column now. So it will move along the column by 1 unit, and then I put a star. So it will give me the value that is stored at this particular currently pointed location. So it is pointing to this. It came to the third row when I did num plus 2, and then I did plus 1. So it moved by 1 unit along the column, and now it was pointing to this 28, to the address of this 28. When I put the star, it will tell me the value that is being stored there. So the value is 28. So this value will be 28. So this is the same as saying num of 2 of 1. Like this and this expression are basically interchangeable. Is it clear? In any case, I have a much more detailed expression at the, I think it's the last question. I'll show that to you again so you can realize it even better there. Okay. All right. Yes. Sorry. Using a single what? Okay. Yeah. No, the address will be printed. So yeah, I have a question. Just wait. The last question that I have is related to that. So I will give you exactly what will be pointed to, like what will be printed if you do with certain things with multiple stars, like this dereferencing operators. Okay, we'll see that at the last question. Okay, yeah. All right, so next we look at bisection method. So this was also covered in the week's lectures. So here what we have is, say we have any function, so f of x. So let me draw any function. So it's like, say this is f of x. Okay, some function of, so y equal to f of x. This is the plot of y equal to f of x. Now what we do, we need to find this root. That means where this we need to find the value of x for which this f of x is 0. So we need to find this x star. Okay, the root. This is the root as in, where the y value becomes, that is the f of x value becomes 0. I need to find that x star. Okay, now that is why this bisection method is used. It is one of the methods that is used for finding roots. Now what we do here is we consider one starting point here, somewhere here, say A, and another starting point at B. So what I am doing is I am taking uh, two initial conditions where one is positive, here B is positive, the value of f of x at B is positive, or should I write, okay, is greater than 0, and f of x equals a is negative. So I am taking two initial conditions like that. Then what I am doing is I will calculate in the first iteration, I'll do the first iteration, I will calculate a new value which is a plus b by 2. Okay, now I'll say that what is the value of f of x at a plus b by 2. Now if it is positive, then I will replace b with a plus b by 2. If it is negative, then I'll replace a with a plus b by 2. So basically what I am doing here is, so yes, yeah, I'm doing that. So so let's say there is a function, some random function, which is y equals to f of x. Okay, and we need to find the root, that is the x star for which f of x is 0. So basically we need to find for what x star this function becomes, the value of the function becomes 0. Okay, so where the function meets the x-axis. Okay, that is the root. So x star is the root. Now what we do in bisection method is we consider two initial conditions, x equal to a and x equal to b, such that they are on opposite sides of the root. Okay, how do we know that they are on opposite sides of the root? At one value, at say x equals to b, the function value will be positive, and at x equal to a, the function value will be negative. That means we know that between a and b, somewhere the function is going to 0. Only then it can go from a negative value to a positive value, right? Because it is going through 0 somewhere. So we take two initial conditions on the two sides of the root, say a and b, some initial conditions, Now in the first iteration what we do is we calculate a plus b by 2. That means we calculate the midpoint of a and b. A and b were our initial conditions and we calculate the midpoint of a and b. So we calculate a plus b by 2. Say it comes somewhere around here. So let's say a plus b by 2 comes somewhere around here. Now here you can see the value is still negative, but it is closer to the root than the value of a. So it is close, this a plus b by 2, even though it is negative, it is closer to the root than the value at a was. So we will forget about this value a and instead we will take a plus b by 2 and b. We always need one positive and one negative value. Okay, so we will just replace this prior negative value that we had, this a, we will replace it by a plus b by 2, which is the closer negative value to the root. And similarly we do the in the second iteration again we repeat that whatever value this has, this was, say it was c. Okay, now we will do b plus c by 2. So now if it say it came somewhere in the positive side, we will replace this b with b plus c by 2. So eventually we'll get closer and closer to the root, such that finally when we do a midpoint, whatever value we get, it will be like the function will be very close to 0 and we can consider that to be the root of the function. Okay, so that is how the bisection method works. Let's consider an example in order to understand it better. So here is the function. So we have y minus e to the power minus y equals 0. So this is our function and we need to find the root using the bisection method. So they have already given us the initial conditions. So let's say this is a function of y. You have y minus e to the power minus y. Okay, so first I'll calculate the value at y equals 0. The value is 0, right? Sorry, the value is minus 1. Right, this will be 0. So this is 1. So this is minus 1, right? Now then I'll calculate the value at y equals 1. How much is that? Can somebody calculate and tell me? Are you sure? It's y equals 1, right? Yeah, 1 minus 1 by e, because this is minus y here. It's not 1 minus, it's e to the power minus 1, right? It will be, yeah, so it will be this, so it will be definitely positive. Okay, so 632, something like this. Okay, now these are our two limits. So this is our a, this is the a, 0 is the a, and b is 1. And you can see that one has a negative value, one has a positive value of the function. That means within 0 and 1, somewhere the function is going to 0, because it is going from negative to positive, the function value. So that means the function is going to 0 at somewhere between 0 and 1. So the first iteration, what do we do in the first iteration? We calculate a value, say c equals 0 plus 1 by 2, that is 0.5. Okay, now we check what is the value of y at 0.5. Can you again calculate and tell me? So it will be 0.5 minus e to the power minus 0.5. So can somebody calculate that? Okay, so minus 0.106. So now you can see that this value is much closer to 0 than minus 1, right? So minus 1, so wherever the function would be 0, minus 1 would be farther from that point than minus 0.106, right? So now we consider this minus 0.106 and the positive value remains the same, so 0.632. So basically we will replace this 0.5 with 0. So because we know now that 0 is farther from the root than 0.5. 0.5 is closer to the root than 0 on the same side. So we'll go for the second iteration where we will calculate this c again, which is basically 0.5 plus 1 by 2. Basically that is 0.75. Okay. Now we calculate what is the value of the function at y equal to 0.75. That will be minus 0.75 this. So yeah, can you calculate this again? 0.277. This is okay. Okay, so now you can see that, yeah, you can see that this is closer to the root than, so this is positive, right? 277, and this is 0.632. So you can say that clearly that y equals 0.75 is closer to the root than y equals 1. So now we will consider 0.75 instead of 1. So in the third iteration we will go 0.5, we'll keep 0.5, that is the negative side, and we will consider this 0.75 as the positive one. Now if you calculate this, how much should this be? Point 625, right? So this should be 0.625, right? Yeah. So now f equals, you calculate the value of f at 0.625 and you will get some value. Now you have to repeat this procedure until you get a value very close to 0. That is, the f value that you will get at that particular root will be very close to 0. So in that case you will say that now this is my like this is my function, like uh, this is my root, and you can already see from the equations already by the third iteration that only one of the options can fit your answer. Okay, because the root whatever you will get, it is calculating each time, it is calculating the midpoint, right? So one of your values is 0.5. One if okay, yeah, we can calculate one more step and then we can say that probably if you calculate this value, what is this value, can you check that? 0.089. So you can see it is much closer, it's a positive value and much closer to the root than 0.75. So in the fourth iteration when you do it, you will consider c equals 0.5 plus 0.625 by 2. Okay, so whatever this is, now you can see that this value will always come between 0.5 and 0.625, right? Because you are doing a midpoint of that, so it will come within this, and the options, in the options only one value can match, is there is a possibility of it for matching because all the other values are greater than 0.625. So you have 655, 665, 656 and so on. So only one value is between 0.5 and 0.625. So you're definitely here, the answer will be option C. Okay, so that, because that is the only answer that is possible here. Okay, yes, calculator will be there. Okay, right. So I hope you understood how to do a bisection. So I have another question for you with the bisection method, but here you do not need to do multiple like till you find the root, because the question asks what is the second iterative value of the root. Okay, so basically you need to do only two iterations. Okay, so the function here is, it's not y but rather t here. So you have the function f of t equals t to the power minus t minus 0.3. Okay. Now your a and b is already given. The initial range is given. So I need to calculate the value of t at 1. So it will be 1 into, so basically e to the power minus 1 minus 0.3. So whatever this will be. And I need to calculate the value of t at 5. So basically 5 e to the power minus 5 minus 0.3. So this is the first step. Then in the first iteration, what we will do, we will calculate the midpoint of 1 and 5, right? So let's do that. So this is 6 by 2, this is 3. Okay. Now we need to find out what is the value of t at 3. So 3 e to the power minus 3 minus 0.3. Okay. So and then we need to check which is the, like, whether it comes in the positive part or in the negative part. Can you calculate and tell me the values here? So first this f of t equals 1. Okay, thank you. And then 5 into e to the power minus 5 minus 0.3. Okay, so you can see one is positive, one is negative. So then next we calculate this, e to the, 3 into e to the power minus 3 minus 0.3. Right. So now you can see it is on the negative side and it is closer to the root than t equals 5. So we'll take 3 instead of 5. Okay. Now when we do the second iteration, what will be the value? We'll take 1, that is the positive part, and 3 as the negative part because it's closer to the root than 5. Okay, so our second iterative value, so the question asks what is the second iterative value of the root? So second iterative value of the root is 2. So answer here is 2. Is it clear? No, here they are asking particularly the second iterative value of the root, not the function, not the function value. It has been written in the note also that you need to find the root, not the function value. So basically this is the root, like this is the second iterative root. It is not the actual root, because if you calculate f of t equals 2, it will not be exactly 0 or very close to 0 maybe. So yeah, but after the second iteration, this is the root that you have found, iterative root that you have found. So here 2 is the answer. Is it okay now? Yeah. Okay. So let's look at the next question then. So yeah, finally we are looking at pointers now. We have already seen one question with pointers, but yeah, let's have a look again. Okay, so what we are doing here, so when we define pointers, we need to put a star in front of them. You have already probably seen that before. So we define, so basically what are we doing here? Which of the following statements is correct? What do you think is the correct statements here? So I can say that if you want to define a pointer, you define it like this, star ptr. That means you are defining this pointer, like pointing to nowhere currently because I have not set where it is pointing to, but this is the declaration of a pointer variable of integer type. Okay, I am declaring a pointer variable of integer type. So it can only point to an integer, to somewhere which stores an integer. Okay, so that is why this int part. So basically this can only point to an integer value. It can point to a memory address storing an integer value. Okay, so now what here we have done, the first part is we have written star x of 5. So basically what we are doing, we write normal arrays. What does that mean? What does this mean if you write it like this? So we are defining 5 pointers here. Okay, so we have here we are declaring a array of 5 integer pointers. Okay, so it is an array of pointers. X is a. Now what about the second one? The second one is also an array of pointers. So the answer here is option B actually. Both of them are ways to define an array of pointers. So basically, what do I mean when I say array of pointers is that there are 5 elements here. Okay, 5 elements, and each has the capability of storing an address. So you can store, say, address 1, address 2, address 3 up to address 5. So basically, you can store 5 addresses in this array. So it is an array of pointers. Similarly, the second one, y, is also the same. So both of these ways of declaration are ways of declaring array of pointers. Okay. Now, what if I do int of star x in bracket of 5? What would this declare? No, this would declare an array, an integer array of 5 elements. So there is the matter of brackets here, like the parentheses play an important role. So if you want to access the pointer, x is the pointer here in this case. Okay, x is the pointer, and star x, this entire thing in parenthesis, this is the integer array, and you are saying that I need 5. So this entire thing represents or declares an integer array of 5 elements. We'll see that in the next question. So for now, just know that if you write it in this way, int star x of 5, it declares the array of pointers. If you write it in this way, star of in bracket y of 5, this also declares an array of pointers. Okay. Now let's see the next question. So here you can see that we have defined some macros. Then we have done this, the what I was just saying in the previous slide. So we have written int in parenthesis star x, then a b c. Okay. Now I am printing the size of ABC. So also I would like to know what would be printed if I print size of x. Okay, and remember that size of an integer and a pointer is 4 bytes. Okay, so that is what has been told in the question. The size of an integer and the size of a pointer is both are 4 bytes. So what is the output here? Okay, so first tell me the output of size of star x, and then tell me the output of size of x. So this will be different. So what I said earlier in the earlier slide is that this declares an integer array of a cross b cross c, this many elements, right? So what are the total number of elements here? So number of elements, if I have to say, is 5 into 8 into 2, which is 80, right? 80 elements. Total number of elements is 80. Now when I write size of star x, that means I am referring to the entire array. So this will basically be 80 into 4. Here 4 comes from the size of an integer, not the size of the pointer. So this will be 320. Now what if I write size of x? If I write size of x, it will only print the size of the pointer, and the size of the pointer is 4. So it will print only 4 here. But here it will print the size of the total number of elements into the size of one integer, which is 4. So total it will print 320. But this will print only the size of one pointer, because x is the pointer. Star x is the array, is the entire array. Is it clear? So here the answer for this question, the answer will be 320. No, it is a declaration of an array, like integer array, not pointer, not a pointer of type integer. It is a declaration of integer array. So you can try out. The star just represents that. I mean, here the star basically does no work because you're basically saying that this x is going to be a pointer to an integer array. So that is why you have put a star x. You could just write simply x and it would still mean the same thing. Okay, so if you instead of this just remove this parenthesis and remove the star, just write x. That would still mean that x is a point. X is a pointer to this particular array. It would have meant that itself. Okay, but here the star x, by saying star x, I'm saying that x is a pointer and it is pointing to an array of this particular size. So when I write star of x, it gives me the array size, but if I write only x, it will give me just the pointer which is pointing to that the first element of this huge array. So it is only the size of 4, but star x, it will give me the entire array. So I think there would be a difference. You can try this out, but if you write only x here, instead of remove the parenthesis and the star, you write only x and you write size of x, it will give you 320. But this way, if you write x, you are saying clearly that x is just a pointer and star of x is the array. You are making a difference between the array and the pointer, like the actual array and the pointer to the array here by writing it in this form. But if you had written say only this int x abc, this is also something you could have written, right? So if you write size of x, it would have given you 320, but in this case it will give you 4. So you're basically you're defining it in such a way that you are making a difference between the array itself and the pointer to the array. Is it a bit clear? No, it will. No, it will not. So that is the thing. I mean, this is a bit of a weird notation of arrays. Ideally, you should try 3 stars, right? Because it's a a three-dimensional point. Like it's a three-dimensional array. So ideally, you should have written like 3 stars. But here, this when you write star of x, it will consider the entire array. Like it's a bit of a weird notation, but yeah, that's what it does. Okay, right. The remaining questions are pretty straightforward. So we are defining a pointer of type integer and a variable a set to 12. Then we are setting this pointer that we have defined earlier to the address of a using this ampersand. This is the referencing operator. So we set the PTR. So now PTR, the pointer points to the address of a. Now we say that star PTR, that is the value stored at this pointer location. We are doing an operation on that. We are saying that star PTR equals star PTR minus twice into star PTR. Okay, so what do you think will be the output of this code? Right. So minus 12 comma minus 12, because you had some value a which was 12. You said I'm having a pointer which is pointing to this. Then you are basically saying that star PTR equals star PTR, which is 12 minus 2 into 12. It is minus 12. But any changes you make to the value this pointer is pointing at will also, I mean, is the same address that A has, right? So you are basically, this pointer PTR is pointing to this address of A. So any changes you make to the value pointing to PTR, pointed by PTR, will change the value stored at this. So this value will become minus 12 instead. So this will go from 12 to minus 12. So the A value will itself also change when you are doing this operation. So the answer will be minus 12 comma minus 12. Okay. Okay. Right. So let's see the next question. This next question is also pretty similar. It's almost the same question. You can just see and answer. Right. So 2,2 is the answer for this. It's the same exact logic that you are doing in the previous question. Alright. Next question, we have two integers that we have defined, integer variables x and y set to 5 and 10. Now we are defining a pointer p which is pointing to x and a pointer q which is pointing to y. Now I am saying that star of p equals star of q. That means the value which was pointed by by q will be stored in the value in the memory location of p. Okay, and then I am saying star of q equals 20. So what when we print x and y, what will be printed? Right. So we have x and y. Now we have p and q. Okay. So this is how it has been defined. Now I am saying that star p is equal to star q. So star p equals star q. What is star q? 10. Right. So this value got changed to 10. Right. Now next I am saying star q equals 20. Right. That means this value got changed to 20. So that means x and y value are now 10 and 20. So 10 comma 20. This is what your answer will be. Okay. Right. Now, okay. So now I was talking about this question. So what would be the equivalent pointer expression for referring to the following array element? So you have an array ARR, which is a 4-dimensional array, and you have I, J, K, and L, these 4 indices. How do you, like, what is the equivalent pointer expression for this notation? So right. So like I said, let's start from the innermost dimension 1, then keep on adding dimension. So we put a star here, add dimension, put a star, add dimension, put a star, add dimension, put a star. Okay, so basically we are breaking down each of the steps. So it's ARR plus I, the first dimension, the second dimension J, go K units in third dimension, go L units in the fourth dimension, and finally give us the value. So the equivalent pointer expression is option B. Now I have already written down what each of these steps will do. Okay, so let's say for a 3-dimensional array, okay, you have say 3-dimensional array ARR, and you want to access this particular element 1, 5, and 3. Okay, so these are the different, I think someone asked the question as to what each of this will do. So if you write just ARR, so this will give you the address of the first element of the array, that is the basically 000 element. Okay, and address of this, I'm just writing ampersand. This is not the right way to write things, but it's just I mean to say that it is the address of the very first element of the array, that is all the 3 indices set to 0. What is the address of that particular element? Okay, so if you write just ARR, now if you write 3 stars and ARR, that means you are asking for the value of the first element, because this is basically the same as saying ARR plus 0 star plus 0 star plus 0 star. This is the same thing, okay, because all 3 are 0. So this is the value of the first element. So it's not the ampersand anymore, it's the value. is the value ARR of 0, 0, 0. Okay, so this is the one. Now what if we put 1 star? Okay, 1 star will mean the address of still mean the address of the first element of the array. So if you write ARR plus 1 giving 1 star, that will mean the address of the second row. So only we will move against the first dimension. So the first dimension is the, say, this is the, this is dimension 1, this is dimension 2, and this is dimension 3. Okay, now we will move one element in dimension by one unit in dimension 1. So here I am saying it's the first dimension is row and second dimension is column, third dimension is, say, height or whatever, like something like that. So we move to the second row of the array when we write ARR plus 1. Okay, so you can think of this array something like this, right? You have this, then behind this you have another something like this, this, so on. Okay, now what I am doing here is I am moving to the second row. So all the second rows. Now I have a potential to move, sorry. Uh, I'm moving to the second row. Okay, so this was the second row. I'm pointing here right now. I can go anywhere into the screen or across the columns. Okay, so I'm going to the address of the first element of the second row of the array by writing ARR plus 1 with a single star. Okay, now these two expressions are basically the same. If you just write plus 5, because this is what we need, right? 1, 5 and 3. So if you write plus 5 with this, or you put a star and write plus 5 and put a star with a parenthesis. This will, both of them will mean that you are going to the address of the sixth element of the second row of the array. So that means you moved in the, okay, I shouldn't write sixth element. Okay, so basically I moved along the column now. So these are the columns, right? So these are the columns like this, right? Now what I did, I was pointing to the entire second row, the first element I was pointing to. Then I moved by 5 units and now I am pointing to the sixth element of the second row of the array. So the sixth element, when I'm saying this entire expression ARR plus 1 star plus 5 star, that means I'm still pointing to the, you know, the first, say, on the let's consider this first sheet, right? The first sheet here. In the first sheet I have gone down by one row and by 5 columns. So I am currently in kind of 1 comma 5, ARR of 1 of 5. Okay, and I am pointing to that element in the first sheet. There are multiple sheets like this behind it. Okay, that is into the screen, say. Okay, so I am at the in the first sheet. I am in the second row and the sixth column. By writing this expression, I am pointing to the address of that. Now if I say plus 3, that means I am now going along the sheets by 3 units. So I am going from the first sheet to the fourth sheet. Okay, so I am going to this particular sheet, this fourth sheet. And I'm pointing to the address of that particular element. So I was already, say, this is 1, 2, 3, 4, 5 and 6. Let's say this is the sixth element. So I was pointing to this earlier, right? Now I go along the sheets to the fourth sheet and I point to the same element here. I point to this element now. Okay, so that is ARR plus 1 plus 5, this entire expression points to the address of this particular element. So I go along the third dimension by 3 units. So I go from 0 to 1, 2, 3. Alright, but I point still to the address. Now if I add another star, that means I'm asking what is the value of this element. So this is equivalent to ARR of 1, of 5, of 3. Is it clear? Like what exactly this pointer notations mean, each step of it? Okay. So yeah, so this is all I have for you today. Uh, if there are any doubts, you can ask me right now. Yes, sorry, one at a time, please. Yeah, because why I said that is because it's a wrong way of writing it. You could just say ARR. Okay, this ampersand symbol is usually used for, it's not used for arrays, because arrays in C, they are defined by references itself. So ARR itself is a reference. If I say ARR like for any array, that means it is a pointer by itself. So writing and of this entire thing does not make sense. At least to me, it does not make sense. So this should make sense if I was just referring to some integer, single integer, or single float or whatever. But writing a ampersand with a array with the entire notation just does not make sense. I could simply say like this, ARR. So this would I could write it simply as ARR. Okay, I don't need to write a ampersand symbol. Okay, that's what I was saying. Yeah. And yeah, someone else was asking something. Bisection method. Okay. All right. So okay. So um, say you have a function f of x. Yeah. I mean, I'm going to explain one of the examples if that helps it to make it clear, maybe. Uh, okay. So this was some function. Okay, some function that we had of t, not x. We had a function of t. Now what we did is we took this initial values of 1 and 5, and we calculated the value of these functions, okay, and we found out that one was positive and one was negative. Now the bisection method is a root finding method. Okay, you can find the roots of a function. What do you mean by a root? Root is basically the value of x for which f of x becomes 0. That is what a root is. The value of x for which f of x becomes 0. The function f of x becomes 0. So basically I need to find the value of t where f of t becomes 0. Okay. Now using the bisection method. Now for that for bisection method particularly, I need two initial conditions on opposite sides of the root. So here the initial condition is 1 and 5. These are the initial conditions. Okay, 1 and 5. Why? Because 1 is on the positive side and 5 is on the negative side. Right? So I can say clearly that the root will occur somewhere between 1 and 5, because the functional value at 1 is positive and the functional value at 5 is negative. So somewhere between 1 and 5 the function must be crossing the x-axis, that is must be becoming 0. Do you agree to that? Yeah. So what bisection method does is that every iteration it calculates the midpoint of the supposed roots. So these are our iterative roots 1 and 5, and we are going to calculate the iterative root after the first iteration, which is 1 plus 5 by 2, just the midpoint. The midpoint is 3. Now we calculate the functional value at 3 and we check whether it's positive or negative. Now we have found here that it's a negative value, but you can see clearly that it has a value closer to 0. The functional value is closer to 0 than we had at t equals 5, right? So it was somewhere. So basically what I mean to say here is that this value of 3, t value of 3 is closer to the root than t value of 5. because the function value is coming closer and closer to 0. That means you are reaching closer and closer to the root. So now what we do is we take this with this value which is closer to the root, that is this t equals 3 instead of t equals 5. The positive part will still remain the same, 1. Only the negative part, because this came out to be negative and this is closer to the root than t equals 5, we'll replace t equals 3 with t equals 5 with t equals 3. So instead of taking in the second iteration, instead of doing the midpoint of 1 and 5, we'll do the midpoint of 1 and 3. So that is what we do. We get the midpoint to be 2, and then we calculate the value at t equals 2. Now if this came out to be positive, say, okay, then and the value would be closer to 0 than 0.067, right? Then we would have considered this 2. For the next iteration we would have done a midpoint of 2 and 3. Instead of 1 and 3, we would have done a midpoint of 2 and 3. Is it clear how this bisection method works? Yeah. So we need to continue doing that until the value comes very close to 0. Say some 10 to the power, you will get values like, it's called the tolerance limit. So you can take a tolerance limit, say of 0.001 or something like this. So finally we'll get a value of which is very close to 0, and then you consider that to be the root. So yeah, so that is how the bisection method works. All right. All right. Any other questions? Array of pointers. Okay. Yeah. So this is basically that. Yeah. These are two ways. These are two ways to define to declare array of pointers. Sorry. Which one are you saying? So, oh, okay, okay. This one. You're talking about this one. Yeah. Okay. So basically, it's just the so this one is not an array of pointers. It is basically an integer array. It's not an array of pointers. Rather, so there is a difference between an array of pointers of type integer and an integer array. Okay. So basically, let's say in our current systems, I think everyone here would have a 64-bit system. The size of a pointer is 8 bytes, okay, and the size of an integer is 4 bytes. So if I write this, that means I am defining, and I check the size of star x, that would give me a size of 5 into 4. That means this star x is an integer array. It's not an array of pointers, it is an integer array, and it has a size of 5 into 4, which is 20 bytes. Now if I write something like this, int star x, no parenthesis, of 5, that means I am declaring an array of pointers, and that would give me the size of this would be 5 into 8, which is 40 bytes, because each pointer is 8 bytes, say in a 64-bit system, in our current systems. Okay, so that is the difference. So this is an array of integers. You are going to store integer values in this array, but in this array you are not going to store integer values. You are going to store memory addresses which point to integer values. Okay, so that is what an array of pointers is for. So you are going to store addresses of integer values, but you cannot store integer values in this, because it is supposed to store only addresses. It cannot store integers, but this array can store integers directly. Is that clear? Uh, that is what that is the declaration. Yeah, this is what I was saying at the end. So if you write it in this form, you're basically declaring it in a way that, okay, normally how if you had declared it as int x of this. Okay, let me talk with this example itself. So if I had said int x of 5, here also I would have declared an array, an integer array of 5 elements, right? This would have also done the same. So if I had have written a size of x, this would have given me 20. Okay, even though just x means it's a pointer to the array, it would have still given me the value of 20. Or let's say one integer is 4 bytes. Okay, so even if I'm saying that this is the array, this is an integer array of 5 elements, if I write size of x, it will give me a value of 20. That means 20 bytes. Okay, but in that other example in here, if I write size of x, this will give me a value of 8 bytes, saying that I'm saying that one pointer is 8 bytes. Okay, so it will give me value of 8 bytes if I write size of x. So basically I'm making a difference between star of x and x. So if I have declared the array like this, star of x in parenthesis and then 5, that means if I am saying x only, it is the pointer. Here also x only, if I say, that is the pointer. Okay, but when you go for a size of function, that you want to know the entire size of the array, this will give you a value of the entire array, while this will give you only the size of the pointer, because star x is the array. Star x represents the entire array and not x. So that is the only difference. But in practicality, you will probably not need to do this. You'll never need to do such a thing probably. In practicality, it's just one of the few things that has been defined in C, but I don't think you will be needing this practically anywhere. Is that okay? Okay. All right then. If there are no further queries, then I'll be closing the session here. Yeah. Thank you. Thank you for joining. We'll meet next. Yeah. You can revisit the lecture again, and also the week's lectures. Just watch the lectures of the week, and then try to do this tutorial again. Probably you'll be able to get some better knowledge, and if you have any questions, you can write in the forum regarding any specific questions that you have. You can put the questions in the forum. The TAs will answer to the best of their capabilities. Okay, all right, thank you for joining, and we'll meet next week on Tuesday 6 to 8 p.m. for discussing week 11 lectures. Right, thank you.